So in this lecture, we will learn how to analyze a continuous beam by moment distribution method. So this is the problem. A continuous beam ABC, support A is fixed, support C is also fixed, and AB span having 30 kilonewton per meter UDL load throughout the span, and the cross section is of 3 times I. And BC member has a point load at 2 meter from C support, and the cross section is of 2I. In moment distribution method, first we have to calculate fixed end moments by considering each span separately. So in this problem we have two spans, that is AB and BC. So first consider span AB. Span AB has a UDL of 30 kilonewton per meter. For UDL, the support moments are WL squared by 12. In anti-clockwise direction at support A, and at support B we have WL squared by 12 clockwise moment. Therefore, MFAB is equal to minus WL squared by 12 because anti-clockwise direction, which is equal to minus 30 into 6 square divided by 12 is equal to minus 90 kilonewton meter. Similarly, MFBA is equal to plus WL squared by 12 because clockwise direction, which is equal to plus 90 kilonewton meter. Now considering span BC, this is the condition for span BC. So for eccentric loading, we have WAB squared over L squared moment, anti-clockwise moment at support B, and at support C we have WA square B divided by L squared, clockwise moment at C. Therefore, MFBC is equal to minus WAB square divided by L square, which is equal to minus 32 kilonewton meter. Similarly, MFCB is equal to plus WA squared B divided by L squared, which is equal to plus 64 kilonewton meter. So once fixed end moments are over, the next step is to find out distribution factors by considering each joint separately. So first consider joint B. Okay, considering only interior joints at joint B, where we have more than one members meeting. Therefore, we have to find out stiffness factor for each member meeting at joint B. Therefore, KBA is equal to 4EI by L because the fore end of BA is fixed. Therefore, 4EI by L. So we have another member at meeting at joint B, which is BC. Okay, and here I for BA, I is 3 times I. That's we have to very careful. So 4E into 3I divided by L is equal to 6 meter, which is equal to 2EI. Similarly, KBC is equal to, here also the for end is fixed, therefore the same formula for EI by L, but I here is 2 times I, so it is equal to 4 by 3 into EI. Summing up the stiffnesses, that means sigma K is equal to KBA plus KBC, which is equal to 10 by 3 into EA. Okay. So next we have to calculate the distribution factors for each member. The general formula is DFI is equal to KI divided by sigma K. Therefore, DF distribution factor for BA is equal to KBA divided by sigma K. KBA is nothing but 2EI and sigma K is nothing but 10 by 3 into EI, which is equal to 3 by 5. So distribution factor for the next member BC is equal to KBC divided by sigma K. Or here we have only 2 members and we know that the summation of all distribution factors at a joint is equal to 1. Therefore, we can calculate 1 minus the DFBA. That from this expression also we can calculate distribution factor for BC. So DFBC is equal to KBC divided by sigma K, which is equal to 2 by 5. Okay. So in this problem we have only one interior joint. Therefore, the distribution factor step is over. So the next step is to start the distribution table. So here in distribution table we have joint, member, distribution factor and FEM. These are the input parameters. So joint A, at joint A we have only one member AB, and joint B we have 2 members meeting at the joint, that is BA as well as BC, and at this joint C we have only CB. Okay. So now we have to fill out the distribution factor for each member and fixed endowment also. So everything filled. Okay. Now the first we have to look out whether we have any hinged support or roller support at ends. In this problem we have fixed support at both ends, that is A and C. Okay, therefore we have to balance only interior supports. Here we have only one interior support, which is B, and we know that for equilibrium condition, each point or each support, whatever it is, of the beam should be in equilibrium conditions. That means there is no balance moment. That means sigma m should be equal to 0. Therefore, in this joint also sigma mb should be equal to 0. But we have different loading condition, and assuming all supports are fixed initially, that's why we have this moment. Okay, for BA plus 90 moment, for BC support, BC member we have minus 32. If you sum up these two, because both are at joint B, if you sum up these two algebraically, we will have some balance moment, which is not accepted in equilibrium condition. Therefore, the balance moment, the extra moment, we have to distribute, okay, according to this distribution factor to each span, so that the joint B will be in equilibrium. There is no balance moment. Now, here plus 90, here minus 32. If you sum up these two, we will get plus 58 kilonewton meter. That is, we have positive 58 kilonewton meter moment extra. For equilibrium condition, there should be some minus 58 moment to be added at this joint, so that we will have zero balance moment. Clear? Therefore, we have to apply minus 58, that is opposite sense, so that we will get now zero net moment. That minus 58 moment at joint B to be distributed to all the members meeting at that joint B as per the distribution factors. That means out of minus 58 moment, 3 by 5 parts should be given to BA member and 2 by 5 parts to be given to BC member. Okay. So that step is called as balance. So for BA member, minus, this is plus 58, the actual no difference between these two. Okay, the extra moment we have at B. Therefore, we have to apply in the opposite sense. So minus 34.8 to BA, that is 58 minus 58 into 3 by 5 is equal to minus 34.8. Similarly, minus 58 into 2 by 5 is equal to minus 23.2. Is balanced. Now, if you sum up all the moments at B, we will have zero moment. That's what balance. So, in balance step, we will have all the joints in equilibrium condition. Okay. Now, because of the application, because we are forcefully apply the moments minus 34.8 to BA member, minus 23.2 to BC member. Once we apply the moment, some of the moment will be carried over to the far end, if the far end is fixed or capable of carrying moments, such as interior support. Therefore, if this is BA member, for BA member the far end will be AB. Okay, AB member, this one. BA, AB. So AB. So for AB is fixed actually, the joint A is fixed, therefore it can carry, carry extra moment. Therefore, half of the this applied moment in balance step will be carried over to this support A or to the member AB. Minus 34.8 divided by 2 is equal to minus 17.4. Similarly, here also, because C joint is fixed, therefore half of the moment will be distributed to CB member, which is equal to minus 11.6. So this is the one cycle over. Okay. So at this step, because of carryover moment, we have to check out whether is there any interior support or not. That is there any interior support getting any carryover moment? Okay, because support A and support C are fixed, it can carry any amount of moment, no problem. There is no need to balance support A as well as support C, since those supports are fixed. But support B is interior support. We have to look at whether any carryover from other joints. In this problem, there is no carryover here. C, B, B. Therefore, in the balance step itself, the joint B is in equilibrium condition. That is balanced. So we can stop the iterative process and we can calculate the final moment. So for the final moment, we have to add all the moments in the vertical column. For example, say for AB member, we have to add minus 90 plus minus 17.4. Similarly for BA, plus 90 minus 34.8. For BC, minus 32 plus minus 23.2. For CB, plus 64 plus minus 11.6. Okay. So finally we get for AB member minus 107.40 kilonewton meter, for BA member plus 55.20 kilonewton meter, for BC member minus 55.20 kilonewton meter, for CB member plus 52.40. Okay. So this is the distribution table step. But in distribution table step, you have to be very careful that if we have done everything correct, then we will get equal but opposite moments at each joint. Okay, if the joint has more than one members. For example, see here at joint B we have two members. Therefore, one member has plus 55.20. Then the next number should be minus 55.20. If we get that value, then we have done the entire process of distribution table is correct. So no mistake done in this step. That we have to check out. Is there some cross check? Okay. So the next step is force calculation by considering each span separately in order to facilitate the drawing of shear force diagram. So considering span AB, the free body diagram. So this is the free body diagram of AB span. Here we have UDL and RA reaction. This is RBA reaction because we have BC member also. From BC member also we will have some reaction, therefore we designate this reaction as RBA. And this is a minus moment, therefore anti-clockwise direction 107.4 from distribution table. Here we have positive moment, that is clockwise moment 55.20. Okay. So we have to analyze this one to find out RA and RB. Just we have to apply the sigma m is equal to 0 and sigma b is equal to 0 to analyze this problem, because this is a determinant structure. Okay. So considering sigma mb is equal to 0 gives this RA into 6 meter, okay, minus 107.4 minus 30 into 6 into 3 or 6 by 2 and plus 55.20 and is equal to 0. So from this we get RA is equal to 98.7 kilonewton. Then applying sigma V is equal to 0, we get RA plus RBA is equal to downward load 30 into 6. Therefore, RBA is equal to 81.3 kilonewton. And the maximum moment, because this is simply supported case, the maximum moment occurs at the midspan, that is in x marked as x is equal to W all squared by 8, because UDL. So which is equal to 135 kilonewton meter, because it is required to draw the BMD. Next, consider span BC and drawing free body diagram. So this is the free body diagram with moments, end moments from distribution table 55.20 negative for BC member, that's why anti-clockwise direction, and for BC for CB member we have plus 52.40, that's why it is clockwise direction, and this is external load 72 kilonewton. Therefore here we have RBC reaction and RC reaction. So determinant structure, therefore we can apply sigma m is equal to 0 and sigma v is equal to 0 to find out the values of RBC and RC. Therefore sigma MC is equal to 0 gives RBC into 6 minus 55.20 minus 72 into 2 meter plus 52.40, which is equal to 0. Therefore, RBC is equal to 24.47 kilonewton. Now apply sigma V is equal to 0 to get the value of RC. Therefore, RBC plus RC is equal to total downward load 72. Therefore, RC is equal to 47.53 kilonewton. Now we are in a position to draw the BMD and SFT. And one more thing, we have to find out the maximum or the simple support moment under the point load. Okay, so using the formula WAB divided by L. So moment under the load Mx is equal to WAB divided by L, which is equal to 96 kilonewton meter. So next step is bending moment diagram. So first draw the elastic line A, B, C, and now we have to mark the support moment first. So at support A we have 107.40 and at support B we have 55.20. So join by a straight line, and for BC member at C we have 52.40. Here also we have to join by a straight line. So this is the negative moment, over which we have to draw the simple support moment. For AB span we have UDL, therefore parabolic form, and the maximum value is 135 kilonewton meter. Similarly for BC we have some triangular distribution. Under point load we have 96 kilonewton meter. So now this is the net moment. Okay, this cancelled by each other. This portion is the shared portion is the net bending moment on the beam. This is negative moment, this is a positive moment, this is negative moment, this is positive moment, this is negative. So this is the BMD for the continuous beam. Now shear force diagram. Now draw the ABC line, that is the beam line. So at support A we have 98.70 reaction, upward reaction. Therefore top you have to mark that the shear as here, and that B, because for the UDL it gradually comes down at 81.3. From 81.3 it will go up to meet point B. 81.3 is the reaction at BA, okay, BA reaction, and similarly BC reaction 24.47. Then at C we have 47.36. But in between we have the point load which is of 72 kilonewton. Therefore 24.41 plus 47.30 is 72. So this is the shear force diagram. So in the next video we will learn how to solve another type of problem.